Dear friends, good evening. This is the third lecture on this series. I have told you in the previous lecture how to find the support reactions for a beam. Now we are going one step further. Now let us see how we calculate the bending moment and shear force for a simply supported beam. So I am considering a beam which is simply supported at both the ends. This time, as the first case, we will see if the constant load is acting on the midspan of the beam. How do we calculate the reactions, the shear force and the bending moment? So as usual, I am considering about 20 kN constant force on this beam. Let us take the span as 10 meters. I'll call the support on the left hand side as A and the support on the right hand side as B. So the first step is to calculate the reactions RA and RB. So this has been explained in the last lecture, so I will not spend much time on finding these reactions. Take moments about A. I'll find RB. So here we are considering this act at L/2, which is 5 meters. 20 kN into 5 meters. RB works out to 20 into 5 divided by 10, which is 10 kN. And to find RA, we consider this equation sigma equals 0, which implies to RA plus RB is equal to 20 kN, and hence RA in this case will be 20 minus 10, which works out to 10 kN. So here RA is 10 kN and RB is equal to. Having found out the vertical reactions, rather RA and RB, it is now very simple to draw the shear force diagram for this. So now let us see how we can draw the shear force diagram. First, I'll draw a horizontal line. I'll continue this vertical line of RA and RB, which represents the extreme ends of the support. So here we find RA, which is a vertical reaction which is acting from down to down upwards rather. So it is in the upward direction from the datum line, what we call this horizontal line as datum. RA rises to 10 kN here. After that, we have a downward force acting at the midspan of the beam, which is 20 kN. In between there is no force, hence the shear force diagram remains horizontal up to the midpoint here. After that, we have got 20 kN force acting downwards. Hence here it is 10, which means the horizontal line which goes below. So this is, say, going all the way, 10 plus 10 will be 20 kN here. So then we do not have any other force again in between, and this shear force diagram closes here because we have got an upward force of 10 kN here, hence the envelope closes. Since this line is above our reference line, it is represented as plus and this as minus, as you can see, there is a change of sign which is occurring below the load point. So let us see what is the significance of this. Now after finding out the reactions and the shear force diagram, now let us see how we can find out the bending moment. As you all know, these two are the reactions, and we have got a vertical force which is acting at the middle of the beam. So obviously the bending moment will be maximum under the load always. So in this case, this 20 kilonewton force is acting at half the span of the beam. Hence, now let us see, I'll call this point as say C. So let us see how we can find out the maximum bending moment. Usually, as you all know, in mechanics, the bending moment is maximum where the shear force changes its sign. Here at the below the load, the plus sign of the shear force diagram is changed into minus. Hence, it is obvious that the maximum bending moment occurs under the load where the shear force is changing its sign. Hence, now we take to find maximum moment. This is the next rather step for us. I'll say take moments about C. This point is exactly under the load. So if we take moments about C, we have one reaction onto the right hand side, and we have one reaction of 10 kilonewton at the equal distance acting at the point A. So we can take moment either onto the right hand side or onto the left hand side, because it is balanced, totally balanced because of the equal distance. Hence, if you take moment about C onto the left hand side, it is RA into the distance, which is equal to 5 meters. So which implies RA we already calculated, it is 10 kilonewton into 5 meters, it gives 50 kilonewton meter. So this magnitude of 50 kilonewton meter actually occurs under the load which we have seen. So for this we can simply draw the bending moment diagram. So this is, I'll call this as SFD, or the shear force diagram. And similarly, I am going to draw a horizontal line here, which is the reference line, and at this point where the shear force changes, this line we find the maximum bending moment. And as we have discussed earlier also, because of these simple supports, at the ends the moment will be zero. Hence, the moment diagram is going to look like this, which varies linearly up to the midspan of the beam and then converges up to the horizontal line over here at the ends. The moment here is zero at the ends, and here this ordinate represents the maximum moment, which is equal to 50 kilonewton meter. So this we are calling that as bending moment diagram. And since the moment is sagging means it tries to deflect the beam downwards. When the beam is deflected downwards, we represent it by a positive sign, and the moment diagram will be positive. This is the usual sign convention. So this is how we are going to find the shear force and bending moment diagram for a simply supported beam with a concentrated load. So let us concentrate more in our next lecture on the different types of loadings, other types of loadings which we come across in our mechanics. And thanks for watching. Please subscribe. If you have any comments, please put in the comment box.